a few logistic announcements. The website for this course is here. On this website, you will follow a link, academics, courses taught, and you will see Magnetism 2016. I will not upload material onto LMS, and communication with the class will take place through a Google Groups mailing list. I will be assisted by my PhD student Ali Akbar. So please share your Gmail addresses if possible with Ali Akbar so that we can do instant communication through Gmail. So magnetism, as you all know, is one of the basic necessities of life. Just like we breathe oxygen, electricity is unimaginable without magnetism. If we did not have the generators that generated electricity, life would be unthinkable. Without magnetism, you wouldn't have fancy refrigerator magnets, but beyond that, you would not even be able to have memory elements, because all your hard disks, all the memory storage devices are based upon magnetic phenomena. Magnetism economically is a multi-trillion-dollar industry. But at the heart of these magnetic phenomena lie basic principles of quantum mechanics, condensed matter physics, and statistical mechanics. So in this course, what we're trying to do is we're trying to understand the underlying mechanism of magnetism so that we can describe and understand two objects. One are magnetic materials, and the other is our magnetic devices. And the underlying principles all stem from quantum mechanics. So what we will try to do in these 4 or 5 months of our interaction with magnetism is we'll try to look at the fundamental principles, and we'd like to bridge the gap between principles and research and materials and devices. So it's going to be a rigorous course. We're going to be fast-paced. The goal is to get you started with research in magnetism. And magnetism is a huge area. It forms the basis of what we call spintronics as well. The spin degree of freedom of an electron is currently one of the most promising aspects of futuristic computing technology. So this is going to be an exciting course, a rigorous course, stemmed within mathematical principles. It will show you nice applications of quantum mechanics, nice applications of statistical mechanics and thermodynamics. And of course, basic electromagnetism is also at the heart of magnetism that we study. I assume that you are all familiar with quantum mechanics, you are all familiar with Maxwell's equations, and you are all familiar with statistical mechanics, because these are going to be the pillars upon which this subject is going to stand. Alright, so any questions about the logistics of the course? So what we're going to start off with is the concept of orbital angular momentum and spin, because this is what forms the basis of magnetism. Remember, from an electrodynamics perspective, whenever you stick a refrigerator magnet, it's special relativity at work. So unknowingly, relativity is a very mundane and terrestrial phenomenon. Whenever you work with magnets, magnetism is describable in the language of special relativity. So I forgot to mention relativity. Relativity is also at work when you're dealing with magnets. And we'll discuss more relativistic aspects when we talk about spin-orbit interactions, etc. So orbital angular momentum, the basic concept which is enough to motivate the subject is, suppose you have a proton and an electron. In the classical model, the Bohr model, the electron, which carries a charge -e, is circulating around the nucleus. Now we all know that the current that is associated with this electron is given by -e times the time period. And if the radius of this orbit is r, which could be taken to be the Bohr radius if this atom is in the ground state, then this current is -e over 2 pi r v, where v is the speed of this electron. Now what I would like to do is, I would like to find the magnetic moment of this orbiting electron. So now what we effectively have is a charge that is oscillating, going around a nucleus, and this revolving charge forms a current. Associated with this loop of current, there has to be a magnetic moment. And magnetic moment is simply a circulating charge. So if the electron is going around this direction, the angular momentum of this electron, which is denoted by L, is in the direction shown. And if we talk about the magnetic moment would be in the opposite direction. This magnetic moment, we all know its magnitude is given by I times the area of the loop. Now the area of the loop is pi r squared. So what we have is -e over 2 pi r v into pi r squared. So this turns out to be -e over 2 r into v. Now if I multiply by m and divide by m, this is the relationship that I get. Now this m is the mass of the electron. So now what we observe is that the magnetic moment is related to the mass, the product of the speed and the radius. And if you know from basic mechanics, could you identify what this object is called? What is MVR? It is the orbital angular momentum of this electron. So this electron has an angular momentum associated with its shear mechanical motion, the orbital motion, and that is proportional to the magnetic moment of this electron. So the magnetic moment turns out to be equal to -e over 2 times the mass of the electron into the angular momentum. And since the angular momentum is a vector, the magnetic moment is also a vector. So this is quite a nice relationship, and this is the starting point for a discussion on magnetism. A revolving charge that carries an orbital angular momentum has with it associated a magnetism. That magnetism is quantified through the magnetic moment. The units of this magnetic moment, of course, are amperes meter square. Remember that we will stick to SI units in this course. So associated with the orbital motion, the orbital angular momentum, there is a magnetic moment. Now we can generalize this statement. Any moving charge Q, we can have the mass of a charge, or we can talk about the mass of an electron or the mass of a proton. So this object multiplied by the orbital angular momentum of this object and some proportionality factor G, let's call it G, will give rise to a magnetic moment. So whenever you have a charged particle and you form this ratio, the charge of that particle divided by 2 times the mass of, for standardization you can talk about the mass of a proton. This quantity has certain dimensions. You multiply this with the orbital angular momentum or any angular momentum and have a constant of proportionality, because this is a measurable. So you perform experiments to measure the magnetic moment, so the constant of proportionality comes either from theoretical motivations or from, and is verified by experiments. So you have a constant of proportionality, which is called the lambda G factor. Then this gives rise to a magnetic moment. The upshot is that associated with an orbital angular momentum, there is a magnetic moment. Even neutrons that are uncharged, the charge on a neutron is zero. It has an orbital or a spin magnetic moment associated with it. There is magnetism, even though it's uncharged. So if you would talk about neutrons, you would put the charge of a proton here and the mass of a neutron here, and you will adjust your value of G accordingly so that you get the correct magnetic moment. The basic principle is that whenever you have an angular momentum, associated with it is a magnetic moment. And what is a magnetic moment? This circulating electron or circulating charge. Let's talk about a general charge. This charge that is moving with a speed v, associated with it is an angular momentum L, and then we have a magnetic moment mu. This orbiting charge produces a magnetic moment, and this magnetic moment can be visualized as a tiny magnet which has a north pole and a south pole. And you can visualize magnetic moments by arrows. So this arrow could represent the magnetic moment. And you can have these arrows pointing in any direction in space depending upon the angular momentum. For an electron, you observe that the orbital momentum and the magnetic moment, they are opposite in direction because the charge on the electron is negative. So now you have, suppose you have a box, and in that box there are electrons. Now each electron may have an orbital angular momentum, and associated with it there could be a magnetic moment. So you have this box of electrons and you have magnetic moments pointing in arbitrary directions. So you can have a soup of magnetic moments. And if it's a gas, these magnetic moments could be pointing in random directions if you don't have any external magnetic field imposed. So you have a soup of magnetic moments. Each one of them could be an electron. Now associated with the orbital angular motion of an electron, there is a magnetic moment. However, we know that mu equals, for an electron, let's talk about general charges. You have a lambda G factor, Q over 2 times the mass of the particle and an orbital angular momentum. For an electron, this Q is minus E. The mass is the mass of an electron, and G is 1, as we just noticed, right? So this is the relationship for an electron. We know that, however, we know that this angular momentum is a quantum mechanical object. So this is really an operator in quantum mechanical terms, which imparts an operator characteristic to the magnetic moment. Right? So orbital, this is an observable. So you can measure the orbital angular momentum. But the electron, if it's in the ground state of a hydrogen atom, for example, if you have an electron in the s orbital, in the s orbital, we know that the azimuthal quantum number is 0. And the orbital angular momentum L, which is given by L into L plus 1, h bar must be 0. So an electron cannot be, in its ground state, cannot be magnetic because its orbital angular momentum is 0. Yet, if you perform the famous Stern-Gerlach experiment, which was performed in the late 1920s by Stern and Gerlach, and they accidentally discovered that the beam of silver atoms in which the valence electron was in the ground state, sorry, the valence electron had an angular momentum L of 0, still it responded to magnetic fields. Therefore, it must there must be some magnetic moment associated with an electron even when L is 0. And this is how the concept of spin was discovered. So now we know that an electron not only has an angular momentum associated with its orbital motion, it also has an angular momentum associated with its spin, which is a purely quantum mechanical phenomenon. So now we have the same relationship. We could have any angular momentum here. We just use the proper value of this lambda G factor to find out the correct magnetic moment. The proportionality holds throughout all cases. Either this could be a spin, this could be an orbital motion. You have to adjust for the proper constant, but the proportionality persists. So if you have an electron or a charge with an orbital angular momentum L, we know that the magnetism associated with this object is going to be equal to G. Now let's put an L with this to denote that this is the lambda G factor associated with the electron, orbital angular momentum, and then you have Q over 2m GS. So now this is a vector, a magnetic moment associated with the orbital and a magnetic moment associated with the spin. Both of these are vectors, and you add them up to find out the total magnetic moment of an electron. Turns out we know that this factor is 1 for an electron. This factor is almost 2 for an electron. The lambda G factor for an electron associated with the spin is 2.002. It's almost 2. This deviation of 0.002 with respect to 2 is about 0.1% deviation from 2, comes out from quantum electrodynamics, and it gives rise to the Lamb shift. But this factor is almost the same as 2. So for an electron, what you have is a magnetic moment which is given by minus E over 2m L plus 2s. This is the magnetic moment of an electron. If the electron has 0 orbital angular momentum, say if it's in the hydrogen atom and it's in the ground state, then the magnetic moment is purely due to the intrinsic spin of the electron. So an electron's spin gives rise to a magnetic moment. So when L equals 0, when L equals 0, the magnetic moment of an electron is minus E over 2m into Gs into S. This is a vector, this is a vector. And this turns out to be minus E over m S. So there's a proportionality between the magnetic moment and the spin if the orbital angular momentum is 0. This constant, which relates the magnetic moment with the orbital angular momentum, is also called the magneto-gyrate ratio. Magneto for magnetism, gyrate for orbital motion. The magneto-gyrate ratio. This is the proper SI name for this ratio. It's also called the gyromagnetic ratio. So whenever you have some kind of orbital or spin angular momentum, we can associate it with some magnetism, a magnetic moment. And that magnetic moment can respond to external magnetic fields. It can interact with other moments inside a solid or liquid and give rise to bulk magnetism and so on. So this is a starting point for a study of magnetism. Orbital or spin angular momentum giving rise to magnetism, giving rise to magnetic moments. Now we would like to see how these spins interact and what are the proper Hamiltonians and how they respond to fields. This is the entire subject of this course. For example, for a proton also has spin. So for a proton we can have a magnetic moment as well. For a proton we have G. For a proton, the charge on a proton time over the mass of the proton into S. So we have to use the proper value of G for a proton. Likewise for neutrons. For neutrons don't have spins. You just plug in the value of the charge on a proton, and replace this with the mass of the neutron. So these magnetic moments are experimentally determinable, and these actually determine what the spins are. So spins are measured indirectly. You do not have a spin meter, a meter that detects spin. You do it indirectly by measuring the magnetic degree of freedom. Magnetism is easy to detect. For example, a magnet will respond to external fields. So you perform experiments with magnets and magnetic moments, that's easier to detect. So this is the underlying principle of magnetism. And this object, by the way, is simply the magnetogyric ratio. The constant of proportionality between the gyric degree of freedom and the magnetic degree of freedom is the gyromagnetic or the magnetogyric ratio. If this is the spin of a nucleus, you can have a spin of a nucleus, then this becomes the magnetic moment of a nucleus. Then it's called the nuclear magnetic moment. It depends on what the nucleus you're talking about. A nucleus will also have orbital angular momentum. Okay, so you have to take that into account as well. For an electron, remember, so if you look at this relationship, for an electron, for a simple electron, okay, let's look at this relationship for an electron. Let's take it further. This is a vector equation, we all know this. This is the mass of the electron. And we're talking only about the spin of the electron. Suppose you just take the z component of the magnetic moment. Now remember, this is an operator and this is an operator. So the quantum mechanical equation corresponding to this is simply U operator is given by minus E over NE S operator. Remember, we're focusing our attention on just an electron, the spin of an electron. Now if you measure the z component of the magnetic moment, you perform an experiment. Remember, whenever you want to perform an experiment, you have to break the symmetry. You perform an experiment by measuring the magnetic moment, but you measure along a certain axis because it's a vector. So you break the symmetry and you measure along the z-axis. You measure along any axis and you call it the z-axis. So if you measure along the z-axis, the magnetic moment that comes out is mu z equals minus E over NE times the z component of the spin. Now this z component of the spin is quantized according to quantum mechanics. So you have minus E over NE ns h bar. Ns is the spin quantum number that can take up two values, plus half and minus half. The spin is quantized, right? So ns could be plus half or minus half. So now you're performing a measurement. You have some magnetic moment associated with the spin of an electron which is pointing in some direction. You don't know which direction it's pointing in. You break the symmetry, you define an axis called the z-axis, and you look at the projection of the magnetic moment along this axis. This is how you perform quantum mechanical measurements. So when you perform this experiment, it turns out that mu z is quantized because this object is quantized. The possible values of mu z are plus minus E. Now this could be half, plus half or minus half, plus minus E over 2 NE h bar. So whenever you measure this magnetic moment of a single electron, isolated electron, not interacting with anything else, you measure its magnetic moment about an axis, you can only get two values. It's quantized. Okay? Now this is a constant. All of these are fundamental constants. Okay? So this constant is called the Bohr magneton. Bohr magneton. Okay? Just like the charge is quantized and you measure charge in units of the charge on an electron, that's a unit of charge. radiuses, lengths are measured in terms of Bohr radius, A0, 0.529 angstroms. Just in the same manner, the magnetic moment is measurable in these quantums, which is, each quantum is called a Bohr magneton. And this gives you the value of the Bohr magneton. So it's like a unit of magnetism. It's like a unit of magnetic moment. Its value is 9.24 into 10 to the power minus 27 ampere meter square. So this is the value of the magnetic moment you would get for an electron, only with its spin. Not talking about the orbital degree of freedom. Alright. Now we know that associated with the spin of an electron or a proton or any angular momentum there is a magnetic moment. Now we would like to do something useful with these magnetic moments. There are three kinds of quantities that we would like to talk about. We would like to talk about what is the energy of a magnetic moment when it's placed inside a magnetic field. That will give rise to different kinds of magnetic materials and different kinds of behaviors. We would like to talk about the energy. When placed inside a magnetic field which is denoted by B, measured in Teslas. We would also like to talk a little bit about what is the force that acts on a magnetic moment. Right? You place it inside the field, what force acts on it. Then we would also like to talk about what are the torques that act on magnetic moments. So these are the three kinds of objects, three kinds of quantities we would like to study, and these will open to us the door of magnetism. We're trying to put our step into the room. We talked about the spin of an electron or proton associated with this angular and spin angular momentum. There is a magnetic moment. Now we like to see how these magnets respond. Remember, each magnetic moment is just like a tiny magnet, just like a tiny compass needle, which can respond to external fields. So it will have a certain energy, a certain force, and a certain torque. Now first, let's talk about the energy of a magnetic moment when placed inside a magnetic field. Now suppose any questions, you can most welcome to ask questions. A small class means more questions. Yes?
So for chargeless particle electron, is this situation still there?
Which?
The energy factor.
Yeah, you then plug in the value of the charge in a proton there and the mass of the neutron. So remember, Gq over 2m is just a constant, which has been defined for an electron and a proton, but then you can divest it from the meaning of a proton and neutron. You can talk about general particles. Okay? You just have to then adjust the value of G. Okay? For a neutron, for example, Q is 0. So you put the mass of the charge in a proton instead, even for a neutron. Now energy. Suppose you have a magnetic field that's pointing in a certain direction and a uniform field. Now all of these concepts come from electromagnetism, and I hope you're all well comfortable with electromagnetism. So this is a uniform field. That field is denoted by B. Now we can represent magnetic moments by arrows. So it's a vector, so you can have a magnetic moment like this, magnetic moment like this, parallel like this. You can have a magnetic moment in an arbitrary direction. And at the back of your mind, conceptually or cartoonically or caricature-wise, this magnetic moment is associated with a positive charge circulating like this, right? A loop. But this is just a naive cartoonistic picture. You cannot draw a picture of a spin of an electron. But if you have a current carrying loop, a physical current carrying loop, the magnetic moment will point like this. For this, there is a current carrying loop with a positive charge circulating in this direction, and so on. and then you don't need to draw these current carrying loops. So remember that each magnetic moment harbors some kind of angular momentum, which gives rise to this magnetic moment. So I will use the word throughout the course magnetic moment, spins synonymously, right? A spin is a magnetic moment. So I will sometimes call these magnetic moments, sometimes I'll call them just moments, sometimes I'll call them spins. Spins is easier to say. Okay. So these are all spins placed inside a magnetic field. Now each of these configurations has a different energy. The energy E of a moment placed inside a field is given by minus mu dot equal B. This is something you learn from basic electromagnetism. It's the negative of the dot product of the magnetic moment and the field. Therefore, this is the low energy configuration. The lowest energy configuration corresponds to this. When you have the moment that's anti-parallel to the field, that corresponds to the highest energy configuration, right? Just whenever they are parallel, energy is negative here. When this is the case, the energy is maximum. And when you have the magnetic moment perpendicular to the field, the energy will be in between. Okay? The energy is given by mu dot B. So the energy is simply minus mu B cosine of theta. So in order to minimize energy, you would like theta to be 0 degrees. So magnetic moments assume a low energy or a ground state if they are parallel to an external magnetic field. Now this concept, when you combine it with statistical mechanics, gives rise to a class of materials that are called paramagnets. Now suppose you have this box which contains a large number of spins. It could be electron, proton spins, and these magnetic moments are pointing in different directions. Okay, in different directions. And upon this box, you impose a uniform magnetic field B. Okay, in a certain direction, and it's uniform. Now different orientations of these magnetic moments will take up different energies. Now if you were to measure the magnetization of this sample, now I've used this word magnetization for the first time. Magnetization is a quantity which corresponds to the bulk properties of the system. It's a macroscopic quantity. It's measurable. It's a macroscopic quantity. And this means you just take the vector sum of all the magnetic moments inside the volume and divide this by the total volume of this system. You get the magnetization of the system. Now if you measure the magnetization of the system, this really means you are defining an axis, and that axis is the z-axis, the axis along which the field has been applied. So you get two possibilities. Either the spin could be parallel or anti-parallel to the measurement axis. This is quantum mechanics at work. But you have a large number of spins. So when you have a large number of particles in an ensemble, you resort to statistical mechanics. You resort to the statistical property of the system. And if I would like to find out the number of, okay, let's suppose that if this is the magnetic field, and the spin is parallel to the field, you call this the state alpha. Okay? And since it's a quantum state, put a ket with it. And if the spin is anti-parallel to the field, you call this state beta. Okay? You could also call this, denote this by this carbon, or you could denote this by this carbon. So these are the two possibilities of spins that you will measure inside the system. So now There are n spins. The total number of spins in this system is capital N. If I would like to find out the fraction of spins that are in the state alpha, how am I able to find out this fraction? What is this fraction going to be equal to? The temperature of this system is capital T. What's the fraction of spins that will turn out to be in the state alpha? Use your basic knowledge of statistical mechanics. Anyone? Yes, yes, it's the Boltzmann relationship. The Boltzmann relationship tells that the fraction of spins in the state alpha is given by the exponent of the negative of the energy of the alpha state divided by kBt, the Boltzmann constant. And for normalization, you have to divide all of this by what? The partition function z. Likewise, if I would like to find out the fraction, remember this is a fraction. This is a fraction. The fraction of spins in the state beta is given by minus E alpha b. And you know what these energies are. These energies are simply this, plus minus mu b. First of all, let's find the partition function for this system. The partition function for this system, z, is given by exponent minus E alpha kBt plus exponent minus E beta kBt, right? This will normalize the fractions, right? This is the partition function for a spin half system placed inside a magnetic field. Now we know the values of E alpha and E beta. So if I go here, z equals exponent. Now E alpha, let's find out E alpha and E beta. E alpha is the low energy state is minus mu b. What's mu for an electron? It's simply the Bohr magnetron, mu b. E beta is plus mu b. So these are the energies of the alpha and the beta states. The magnetic moment of a single electron with just a spin is the Bohr magnetron. We've already derived that. So we know what the energies are. So we can simply plug in these values. This becomes mu b b over kBt plus exponent minus mu b b over kBt. This is the partition function, and this is nothing but 2 times cosh of mu b b over kBt. Okay, so we've derived the partition function. This is the partition function for a spin half inside a magnetic field. The field has magnitude b, the system is at temperature T. Just coming out from the Boltzmann distribution. Now we can find out N alpha. N alpha and N beta are simply given by exponent mu b plus minus mu b b over kBt divided by 2 times cosine of mu b b over kBt. Right? So for N alpha you have plus mu b b over kBt. For N beta you have exponent minus mu b b over kBt. Okay. Now we have found out the fraction of spins which are in the state alpha and the fraction of spins which are in the state beta. Now is this system magnetized? First question, yes or no? What is the condition for this system? Even though the particles in the ensemble, each one of them is a moment, is it possible that this system is unmagnetized? Can this be zero? When can this be 0? When the sum is 0. But the magnetic moments are either parallel or anti-parallel. So this can be 0 only when half of the spins are in the alpha state and half of them are in the beta state, because alpha is up, beta is down. And that can only happen at infinite temperatures. Okay? So this system will have some magnetization. So what's going on is that the alpha spins are creating a magnetic moment in one direction, and the beta spins are creating a magnetic moment in the opposite direction. And if there is some net difference in the number of these spins, will there be some residual magnetic moment or magnetization of this sample? Okay, so if I would like to calculate the magnetization of this ensemble of spins M, just the magnitude, what would I need to do? If my spins are in the state alpha, what is the moment of each spin? Mu b. Mu. But I have n alpha spins. So n alpha spins, each one of them has a moment mu b. So this is a fraction. I multiply this with the total number of spins. This is n into n alpha is the number of spins in state alpha. I divide this by the volume. The number of spins in the state beta is n into n beta. What's the moment of each spin in the state beta? Minus mu b. So I have minus mu b and I divide by the volume. This is the magnetization of the sample. The magnetization turns out to be n mu b over b and alpha minus n beta. And if you plug in these values, this turns out to be n mu b over b into tanh mu b b over kbt. Because if you do the subtraction, exponent mu b b kbt minus exponent minus mu b is the sinh function. You divide this by the cosine function, you get the tanh function. Now, unfortunately, the computer isn't working because we don't have the proper cable. I'll show this to you in the next class. But this is the magnetization of an ensemble of spin half particles at temperature T, placed inside a magnetic field B. Okay. And if you notice, we can simplify this further. The magnetization, this n over b is just the density of spins. I denote this by small n. Mu b is the moment of each spin, tanh mu b b over kbt. We can plot this. I can show this to you on a computer, but not today. And if you would like to plot this, now this quantity here, n, small n into mu b, what does this physically mean? What does this physically correspond to? In one direction, divided by the volume, this will give you the magnetization at 0 Kelvin or magnetization at infinite field, which means that all the spins are pointing in the same direction. Then the magnetization of such a material will be n into mu b. So this is like an upper limit to the magnetization. When all the spins are pointing in the, so if you had this ensemble in which somehow the field was applied in this direction, B, and all the magnetic moments were also pointing in this direction. This of course can only happen if the field is infinite or the temperature is 0 and at some finite field. So then the magnetization of this sample will be n times mu b, and this is simple to understand. Mu b is the moment of each spin and the number of spins per unit volume is n. So this is called, this object is called the saturation magnetization. So this n into mu b is ms. So I can put m over ms, where ms is the saturation magnetization, or the maximum possible magnetization. This is given by tanh mu b b over kbt. So if I were to plot m over ms versus this factor, right? This factor is mu b b kbt. Let's call this x. So this goes up when the field goes up, or the temperature goes down. When temperature goes up, x goes down. So if I plot this function, this is what the tanh function looks like this. This can also be negative, because the field can go in the negative direction. It's continuous here. Okay. This is what the tanh function looks like. At some field over temperature, when this value is large, V over T is large, when field is large and the temperature is small, then this magnetization reaches its saturation level. This is 1. This is -1. Before that, it has a tanh appearance. Okay, and in the field is applied in the negative direction. You can't have negative temperatures, by the way. Statistical mechanics says you can, but for the moment, let's assume you can't have negative temperatures. The field goes in the negative direction, the magnetization goes in the opposite direction. You saturate at a certain negative field. So such a kind of material is called a paramagnetic material. Okay. If you have spins which are not talking to one another, all of them are isolated. We're talking about isolated magnetic moments for the time being. So these are all isolated magnetic moments. And the first week will be spent talking about isolated moments. So this is the hallmark of a paramagnetic material. As the field goes up or the temperature goes down, the magnetization goes up. Okay. Now we can make certain symmetry. Remember, we're talking about spin half particles. These are quantum mechanical particles. Spin is quantized, and if you have a soup of them, an ensemble of them, the sample macroscopically attains a magnetization. This is called the macro spin assumption. The entire sample is now determined by a thermodynamical variable, which is the magnetization, which is measurable, macroscopic. You can measure this magnetization using experiments. That's what you do all the time. Now there are certain approximations you could make, certain interesting approximations. Okay, just one thing, if I had a computer, it would be better to show that if I were to plot m over ms versus 1 over x, that is versus kBt over mu bb, the kind of graph that I will get is like this. Okay, so if I plot versus 1 over x, this is what I will get. As the temperature goes up, the magnetization drops. This you could do in Mathematica or any software of your choice. Now let's look at the high temperature approximation. Now I'm saying that x I'm defining as mu bb over kBt. So my magnetization m over ms is tanh of x. So in the high temperature approximation, I think this goes to x. Let's see if that's true. So tanh of x, high temperature means x is defined as mu bb over kBt. High temperature means small x. So tanh of x is ex minus e minus x over ex plus e minus x, in the limit that x goes to 0. X is small. This thing turns out to be x. Okay? You just expand each exponent with Maclaurin series. So m over ms, in the high temperature approximation, which means really, what do you mean by high temperature? This really means that kBt is much larger than mu b p. Okay, this is the high temperature approximation. Under these conditions, x is going to be really small, it's much smaller than 1. So, by small and large, whenever you use small and large in physics, you have to qualify the statement. What is meant by small? What is meant by large? There's no absolute small or absolute large. You all know that. So in this approximation, m over ms is x, which means that m equals n mu b. This x is, you get this, right? In the high temperature approximation. Now if this material is linear, then the magnetization is given by the magnetic field intensity H, which you learn from electromagnetism. I'm not going to describe this, and a certain constant of proportionality is called chi. This is called the magnetic susceptibility. Right? The magnetic susceptibility. So for linear materials, m is proportional to h, and proportionality is called the susceptibility. This is the magnetic susceptibility. There is an electric susceptibility as well. In the electric susceptibility, you have an electric field here, and you have epsilon naught for dimensional consistency, and you have the polarization here. But for magnetism, this is the magnetization is proportional to h. Okay, but h is b over mu naught. Okay. For a paramagnetic material, in the common sense usage of the word magnetism, a paramagnetic material is non-magnetic. That's the common sense parlance. In common day language, a magnetic material is just a ferromagnetic material or a ferrimagnetic material. Common day usage, magnetic material is water, is diamagnetic, it has some magnetic properties, but in common day language, what is non-magnetic? Copper is non-magnetic, but it's really diamagnetic. Aluminum, diamagnetic. Okay. So paramagnets are non-magnetic in the common day usage of the English language, but they really have certain magnetic property, and that is paramagnetism. For paramagnetism, for such materials, B equals mu naught H. Why? Because B really equals mu naught H plus mu naught M. This means mu naught H plus mu naught chi H. Now for paramagnetic material, this chi is much smaller than 1. Okay, it's really small. Therefore, for such materials, you just ignore this term. So B turns out to be equal to mu naught H. So for such materials, if I insert these values in here, M equals chi H, but H equals B over mu naught. And this equals, in the high temperature approximation, N mu B square over B over kBt. And if I do the fortuitous cancellation, this B goes away, okay, and I'm left with the value of the susceptibility of such a material. This is N, number of spins per unit volume, mu naught, which is the permeability of free space, mu B squared over kBt. So the susceptibility turns out to be, for a paramagnetic material, this is what it turns out to be. And it's inversely proportional to the temperature. Higher the temperature, lower will be the susceptibility. So lower will be the magnetization. This is called the Curie's law. famous Curie's law. And if I were to plot for a paramagnetic material the temperature dependence of the susceptibility, what will this graph look like? What is it going to look like? If I just plot, okay, just this is a constant, everything is a constant. If I plot chi versus T, what is it going to look like? Inverse, how do you plot this? Do you plot only chi versus T? It's not going to be a straight line. Yes. It's not going to be a straight line. Remember that this is something very basic. You should know this. This is a hyperbola. If I were to plot, this is the Curie's law. If I were to plot chi versus 1 over T, this is going to be a straight line that passes through the origin. Okay? Large temperatures, susceptibility drops. At low temperatures, it diverges to infinity if the material remains paramagnetic at such a temperature. So this is what, so if you are able to measure the susceptibilities through some experimental technique and measure it versus temperature, you can determine whether it's a paramagnetic or diamagnetic. Or in condensed matter physics, most material properties are determined by looking at the temperature range. You vary the temperature, you get to know what the material is. So one of the most important, the first experiment an experimenter would perform to determine a material is some temperature dependent property. Likewise for magnetism. Any questions?
So sir, speaking in the general sense before, generally we are introduced to magnetism first and the quantum mechanics between. And so for paramagnetism we know that susceptibility is much less than 1. But sir, quantum mechanically speaking, and now that we have a macroscopic picture of an ensemble, what is it that makes this ensemble paramagnetic and not some other thing? Is it the property that there will be two possible spin states? That what makes it paramagnetic?
No. If you have an isolated magnetic moment, okay, not interacting with anything else, and it's in the ground state, you can either have paramagnetism or diamagnetism. For other more interesting properties, you need interactions. But every material that you can think of has some intrinsic diamagnetism as well. But in some cases, the paramagnetism effect masks the diamagnetism. It overcomes it. Every material will be diamagnetic. But you have an isolated electron, gas of electrons which is independent, it's always going to be paramagnetic. So you add some kind of interaction, you turn on interaction and you get other interesting behaviors. There has to be some kind of interaction. Now we know that the spin half system is just one of the many possibilities. What could be the spin of a particle? What are the possibilities for the spin? Spin half is just the tip of an iceberg, it's just one kind of particle. What could be the spin or the angular momentum of a particle? What quantum numbers are allowed? What could be the value of J, the quantum number? Could we have a spin which is 3 by 4, 5 by 16? You classify particles into fermions and bosons. So the spin could be 0, half, 1, 3 by 2, 2, 5 by 2. So it varies as multiples, integral multiples of half. And if it's an integral multiple of, an odd integral multiple of half, it's called a fermion. Otherwise it's called a boson, right? We all know this. It's basic physics. Now suppose remember we are just within the energy manifold, we're just talking about the energy, and from this energy description, we've out of this has popped the idea of paramagnetism. So far we haven't talked about forces or torques. So the idea of paramagnetism has just popped out of a consideration of energy of a dipole placed inside a magnetic field. Now you could also have J, value of J which is 0, half, 1, 3 by 2, 2. There's nothing special with the spin half particle. Remember, okay, one thing I forgot to mention for spin half particle, you know that we talked about the two states, one is the state alpha, one is the state beta, spin parallel to the field, spin anti-parallel to the field. So one description that is quite popular is to draw an energy manifold. So this axis is the energy axis. And you have two states that are separated by a gap. And this gap is 2 mu b p, right? This energy is minus mu b b, this energy is plus mu b b. So this spin half particle is actually a quantum two-level system. And you can drive transitions between these states. You can shine radiation. And you can get an excitation from the ground state to the excited state. What kind of radiation depends upon this energy gap? This energy gap is h bar omega. Every energy gap is h bar omega. So the frequency of the radiation is determined by the magnetic field. For electrons at normal fields of say 1 Tesla, 1 Tesla is a large field. This frequency is in the gigahertz range, in the microwave regime. If you talk about protons at a field of 1 Tesla, this frequency is 40 megahertz. So you use radio waves to induce transitions between these states. For electrons you use microwaves. This is how the entire field of molecular spectroscopy is determined by energy separations. So you can excite states and they will fall down into the ground state and they will emit radiation. Okay? So there's an energy gap. And this energy gap is going to increase if the field increases. The field keeps on increasing, the gap keeps on increasing. And the population is determined by how big is this gap with respect to the thermal energy, kBT. If this gap is big with respect to kBT, then the lower state is going to be preferentially populated. If this gap is small, thermal excitation is going to excite the spins as well. At infinite temperatures, would you get an equal population? Okay, so this is basic statistical mechanics. It all applies to magnetic materials. In fact, I'm going to do a special lecture on thermodynamics of magnetism. This is a subject that's not very well understood. Now let's talk about an arbitrary angular momentum state, J, right? Now the energy of such a system is again given by minus mu dotted with B. Now likewise, the magnetic moment, the Z component of the magnetic moment is given by some lambda G factor, and I put a small j with this, which means I am talking about some spin J, Q over 2m, okay, S of Z, and now I talk about J of Z. Now J of Z is quantized in terms of mj h bar. Right? Now let's call this object. Let's suppose that we're talking about, we put the charge on a proton here, the mass of an electron here. So this thing turns out to be equal to mu b, the Bohr magneton. So the magnetic moment is given by Gj mu b mj. Okay, where mj is quantized. If we have an angular momentum quantum number j, what are the allowed values of mj? What are the allowed values of mj? Basic quantum mechanics, basic atomic structure. Are you master students? MP students? What are the allowed values of Mj? If you have a quantum number, okay, let's talk about the hydrogen atom. Hydrogen atom is easy. If L is 1, if you are in a p orbital, L is 1, what are the allowed values of Ml? Then L 1 है, 1 है, p orbital में इलेक्ट्रॉन, Ml की क्या वैल्यूज हैं पॉसिबल? कितनी तरह के p orbitals होंगे? हाँ, 2 नहीं होगा. L अगर 1 है, 0, 1, -1. If L is 2, you have 2, 1, 0, -1. These are the allowed. These are the azimuthal quantum numbers. So if you have an angular momentum J, which could be one of these values, and the possible values of Mj are -J plus 1, because of the rainy weather, these chalks have become slightly damp. Okay, all the way up to J minus 1 and J. Okay, so these are the allowed values of Mj. And how many are they? How many are they? What is the degeneracy of the jth quantum state? How many are they? 2j plus 1. These are 2j plus 1 states. Okay? You can talk about, think about the hydrogen atom. If you have a d orbital, in a d orbital L equals 2. So there are 5 possible d orbitals. Between the L can take up 5 values. If you are in a f orbital, you have 15 possibilities, right? 7 possibilities. So these are the allowed values of Mj. Mj is quantized, okay, which means that the magnetic moment is going to be quantized. For an electron, this is simply m. This is plus half or minus half, and this is 2 for an electron spin. G is 2. But for an arbitrary spin, this could take up any value, Gj. Right? Now, and in fact in atomic physics you learn what this value is going to be. It depends upon L and S. You learn what you can derive this value from first principles. Anyway, the energy of a spin J particle, arbitrary spin J particle, is given by minus Gj mu b Mj b, right? The same principle as we've done for spin half particle. Now we use the Boltzmann distribution once again and an ensemble of spin J particles and find out the paramagnetism for such an object. We can do that, right? You have isolated spin J particles not interacting with another. It's another paramagnetic system. Only that it's not a spin half system, it's a spin J system. And let's do this. So let's first find out the partition function, Z. We know the energies. The energy in the jth level, okay, in the njth level is given by this, right? So the partition function is given by exponent minus the energy. Now what's the energy? The energy is minus becomes plus Gj Mj mu b over kT, and you have to sum this, right? Over what values? Mj goes from minus j to plus j in steps of 1. Okay, in steps of 1. Now this is a geometric progression. So you can find out this sum. So exponent let's call all of this x. Okay, so this is exponent mj x summed over all possibilities of mj minus j plus j. Now this is a finite series, so I get exponent minus jx 1 minus exponent 2j plus 1 x 1 minus exponent x. Supposedly this is what I get, sum of a geometric series. Sum of a geometric series is a naught r n r r m is given by a naught 1 minus r m n, right, divided by 1 minus r n, right. So you use this geometric series. This is the partition function. Now I leave the other calculations for you, but let's work out what the magnetization of this material is going to be. Now if the particle is in a state mj, what is its magnetic moment? Its magnetic moment is here. This is the magnetic moment for a particle in the state mj. So if a particle is in the state mj, its magnetic moment is gj mu b mj. Now we need to find out the fraction of particles in this state. The fraction of particles in this state multiplied by the total number of particles divided by the volume. Now the fraction of particles in this state is simply the Boltzmann factor, exponent minus the energy. The energy is, with the minus sign, this becomes gj x, gj, let's call it mj x, okay, divided by the partition function, which is exponent minus jx 1 minus exponent 2j plus 1 x divided by 1 minus exponent x. Okay? So this is the magnetization of such a material. And of course you have to sum over all possibilities of mj. Alright? Now this is something that I would like you to do on your own. You will notice that this z, if I have exponent mjx divided by z, this is related to the partial derivative with respect to x of natural log of z. So just try to do this on your own, and the textbook, which also has a derivation. So what the final result that you get is a magnetization whose ratio with the saturation magnetization, which once again is going to be, when all the n spins are pointing in the same direction, is going to be given by a function which is called the Brillouin function. And this turns out to be 1 over 2j plus 1 cotangent hyperbolic 2j plus 1 over 2x, where x is, I've already defined x, minus cotangent x over 2. This is called the Brillouin function. So please derive this on your own. It's imperative that you are able to make this derivation. It's extremely important. Since it's an advanced level course, a lot of work will have to be done on your own. So in the next class, when the computer is working, I'm going to plot this function and compare it to the spin half particle for different temperatures. In the next lecture, what we're going to do is we're going to see how magnetic moments and spins respond to magnetic fields. How can a force act on a magnetic moment? And this has a lot of applications. For example, magnetic nanoparticles, when they are administered to the body, so that, and the desire is to make nanoparticles, which are magnetic moments, giant moments, go to a certain region, which is the cancerous region. They have to be steered by magnetic fields. Right? So a magnetic field must be applied. But it turns out that if you apply a uniform magnetic field, no force is going to act on a moment. You have to apply non-uniform fields. Then the famous Stern-Gerlach apparatus experiment also applies a non-uniform field to separate out magnetic moments. How do we know that the spin is half? It's by performing the Stern-Gerlach apparatus. How do we know that the spin J is 3 by 2? Perform a Stern-Gerlach experiment. Right? Then I would like to talk about torques. And I would like to give a block picture of what happens when moment is placed inside a field. It experiences a torque and then it relaxes to a ground state. And this is a very important concept for the idea of spintronics. The first week we're going to talk about isolated magnetic moments only, no interactions, but we're building the basis for a strong understanding of magnetism. Thank you very much.